So let's look at a full example of a discrete Fourier transform. Now we're going to do the discrete Fourier transform of this sine wave here. So if you've done the Fourier and Laplace transforms course, you'll have seen this derivation here. So if you're unsure, I suggest you go back and have a look at that video. But what we've got here is our sine function in the time domain, and we've got the Fourier transform of it here in the frequency domain. Now this is a purely odd function, so it means that there's not going to be any cos omega t part of the e to the I omega t. It's going to end up as a value of 0. So we're only going to end up with one part of the e to the minus I omega t surface. So this is purely to the sine omega t surface. So what we would have in terms of a Fourier transform would be this function here, modulating this surface, and then we would be integrating it in this direction, that is integrating with respect to time. Now in the frequency domain, what we're going to get are two spikes. There's going to be one at a value of plus omega naught. So in this instance, the example we're going to do here is 1 Hertz. So there's going to be a spike at 1 Hertz, but there's also going to be a spike at minus 1 Hertz. And one will be a positive spike and one will be a negative spike. So this here is the Fourier transform of the sine omega, the sine function. So written out in full detail here, the Fourier transform of our sine omega naught t is going to be the delta omega minus omega naught. So that's going to be this pulse here, and you can see it's an imaginary as well. It's going to be a value of I. The height of this one here is going to be pi, and it's minus. And this other pulse is given by this part here. So this pulse here is going to be the delta omega plus omega naught, or in this instance it's going to be minus 1 Hertz. So you can have a look at this in MATLAB as well, and I'll show you the MATLAB output. So I've left the MATLAB file there for you to go and recreate this if you want to. So we have a sine function here, and the Fourier transform of it is shown above. Now this sine function has been cut off at this point and this point here, so obviously it doesn't go off to plus and minus infinity. It only goes off to a value of minus 10 and plus 10. So you're going to get these little ripples here. But in effect, what we can see here as the Fourier transform, we've got a pulse at minus 1 Hertz, and we've got a pulse at 1 Hertz, and they're purely imaginary. One is positive and one is negative. Now it's not really surprising that we get that, because from the Euler identity we had that e to the I theta is equal to cos theta plus I sine theta, and e to the minus I theta is cos theta minus I sine theta. So it means that we can create these two identities here just simply by adding these together. So you can see that the sine theta identity has got two complex exponentials in it. So in effect, one of these exponentials is one of the spikes, and the other exponential is the other spike. And you can see here that one of them's got a negative value, and one of them is rotating in one direction, the other is rotating in the opposite direction. And you can see that this here generates the sine function, because if you were to draw out each of these rotating phasors, you would have the e to the I theta, which is this one here, rotating in this direction, and e to the minus I theta would be this one here, rotating this direction, but it's actually minus e to the minus I theta. So the actual vector position of this one here is in the opposite direction. It's a vector value, so it's going to be a minus e to the minus I theta, that should say there. So that's going to be rotating this direction. So when these two here rotate in opposite directions, the vector summation of them will be this pink line here, and this pink line here is mapping out the sine function. So it's hardly surprising that we actually get two pulses in the frequency domain, and you can see that in the next little simulation. Again, these simulations you'll have seen in the Fourier and Laplace transform course if you did that course. So what we're going to go into next is we're going to extend these ideas here, and we'll extend them to the discrete Fourier transform. So what we've got here is our circle. We've got our two phasors here, one in blue, which is e to the minus I theta, travelling in the clockwise direction, and we've got one in the orange, which is e to the I theta, which is travelling in the anti-clockwise direction. And we can produce the vectorial sum, so that you can see the vectorial sum of these two lines here, which maps onto a point on the y-axis. Now, as these points move round, this point here will move up and down this line from +2 to -2. So let's just see that happening. And you can see that, if I bring it back to that point here, you can see that happening here. So it's going from -2 to +2, and it's a vector addition of those two rotating phasors. So that's mapping out twice the sine. So the sine's going to be half of that. So we've seen what we do with the discrete Fourier transform is we take the sine function. Now this sine function actually goes off to infinity in this direction, and say it goes to infinity in that direction. But of course, when you're doing real signals, you don't have the luxury of dealing with infinite time. So we're going to sample this function over one period. So in this instance here, we're going to take 8 samples. So the samples start here from sample 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that's 8 samples in all. From 0 to 7 is 8 samples. And then what would happen is that this sine wave would go back to that pink point there, and then it would repeat again. So what happens is these samples here, the height of them is going to modulate our sine omega t surface. Of course, it's not sine omega t in the sense that omega is a continuous function. It's actually going to be a discrete function, so it's actually going to be the discrete indexes of k, and also in the time domain it's going to be the discrete indexes of n. So it means that this surface here, which previously when we looked at it in terms of the Fourier transform was a continuous surface in both frequency and in time, and then when we looked at it in terms of the discrete time Fourier transform, it was discrete in time, so it was discrete in this direction, but it was continuous in the frequency direction. And then when we looked at it in terms of the discrete frequency Fourier transform or the Fourier series, we had it as discrete in the frequency domain, but continuous in the time domain. So finally, we decided to make it discrete in both domains. So now it's discrete in both domains. All we have really here are these little points, if you like, little needles sticking up. That's all that's left of this surface. So we can see the forward transform equation that we derived up here. Now what we're going to do is we're going to go from the time domain, Fn, to the frequency domain, Fk, and we're going to go through this surface. So what happens is this function here modulates the surface, but the function only exists at these points. So these points here modulate the height of these little spikes. So for example, the value 0 here, the 0 value will modulate these 8 here. This value here, which in this point here is actually going to be 1 upon root 2, that's going to be the height here, because we've split this into pi by 4, so this is going to be 1 upon root 2. So that'll be 1 upon root 2 that would modulate these 8 here, and then there would be a value of 1 which would modulate the next lot, and there'd be a value of 1 upon root 2 which would modulate the next lot, and a value of 0 which would modulate them, and so on and so forth. So each of these values here, the 8 values, are going to be modulated by the height of this sine function at those points. So that's this part of the function here. The values f of n are going to modulate the surface, and the surface is given by this part of the equation. Of course, as we've noted here, we're actually only going to need the sine omega t part of that surface, but it doesn't matter. We'll actually go and we'll calculate the cos part of the surface as well, and we'll see that it does actually equal 0. So we'll do that in the next page. So finally, after we've multiplied f of n with the surface here, we're going to have to sum up the values from n equals 0 to n minus 1. So the n equals 0 is this point here, and n minus 1 is going to be the last point here. So we're just going to add up these 8 here. And when we sum up these 8 here, it's going to give us the value for the discrete Fourier transform for that point 0. So we'll call that there a bin, and that's bin 0. Now, that's us taking that for a value of k is equal to 0. Then what we do is we move along to the next point here when k is going to be equal to 1. So at k equals 1, we then go ahead and we sum up from n equals 0 to our value of n minus 1. So we add these up and it gives us this value. And then we head on to the next one along, which is k equals 2. So we get a value of k is equal to 2 in here. And then we sum up the values from n equals 0 to n minus 1. So we add up these 8 values, and so on and so forth. We add up these 8 values, and then these, and then these, and finally with this final lot here. And this is going to give us our discrete Fourier transform. So from our derivation of the discrete Fourier transform, we've seen that we're going to get a discrete and periodic function. So the discrete Fourier transform would give us one phasor here at plus 1 Hz, and it would give us one phasor as well at minus 1 Hz, which I haven't drawn in here. I didn't want to clutter it up, but it would be a phasor and it would be pointing in this direction here. Now those two phasors would again repeat because, as we said, the discrete Fourier transform is inherently a periodic function. So it's going to give us another set of rotating phasors here, and again they're going to be separated by 1 Hz. But this upper band here, the lower part of it is actually going to be impinged here on the diagram, so we're actually going to get that there sitting at bin number 7. Now the same thing would happen in the negative axis if we had such a thing as our negative frequency. Further up that axis we would get this repetition here, and if we were to take this to the extremes, then these would repeat off to infinity in both directions. But of course the DFT is inherently practical, so we're not interested in things tending off to infinity in either direction. We're only interested in what happens within a small time scale. So we can see here then what we expect to get within this small time scale is one phasor here at bin 1 and another phasor up here at bin 7. So another thing to note here is that the terminology, we tend to call these bins. Okay, so this is where the energy has all been located at these particular points, which we call bins. So if I shall put the values in, we're going to get a value of minus 4i at this bin and a value of 4i at this bin. So we're going to be left with just these two spikes. So let's go ahead and we'll actually do the mathematics and we'll actually derive these values. So let's put the values in and we'll work this discrete Fourier transform out. So we'll start off with k equals 0, then we'll move to k equals 1. So don't get lost in this. All we're doing is we're starting off at the value k. So this is our k. So our k is equal to 0 and we're adding up these 8 terms. And then we're going to go to k equals 1 and we'll add up these 8 terms. So let's do the k equals 0. So the equation is f of 0 is going to be equal to the sum from n equals 0 to n minus 1 over f of n e to the minus I 2 pi. Now the first one here is the k and the second one is the n. So we said that the k is equal to 0. So that's the same as saying e to the power of 0. Now anything to the power of 0 is just 1. So that's the same as saying sum from n equals 0 to n minus 1 of f of n. So all we're doing is just adding up the first 8 values. So if we head up above and have a look, all we're going to do is add up the heights here. So it goes 0, 1 upon root 2, 1, 1 upon root 2, 0, minus 1 upon root 2, minus 1, and minus 1 upon root 2. So we're just going to add those values up. So when we add those values up, you'll see that they come to 0. So that means that f of 0 is equal to 0. So now let's go and do it for k equals 1. So up above here, we're adding up the k equals 1, so it's this lot here. So when k equals 1, we can say f of 1 is equal to, well, the first value is going to be the value of the fn. So the fn here, in this instance here, is just starting off, it's the values of 0, 1 upon root 2, 1, 1 upon root 2, 0, minus 1, minus 1, and minus 1 upon root 2. So these are the numbers here that's going to be multiplying our e to the I, e to the minus I 2 pi kn upon large N. So we're going to have 0 times e to the minus I 2 pi times 1 for the n, and 1 for the k, and 0 for the n, all divided by 8. And then you're going to have the fifth number here, e to the minus I 2 pi times 1 for the k, and now 1 for the n. And we do this all the way along, and we keep the index k at 1, and then we just change the value of n. So n becomes 2, 3, 4, 5, 6, and 7. So these are our values here for our f of 1. So now we replace the value e to the I theta with our identity, which is e to the minus I theta will equal cos theta minus I sine theta. So we'll replace this here, we'll have 0 times, and this gets replaced with cos of the angle, that angle there, that's going to be 0, minus I sine of 0. And we do the same with the next one, it's 1 upon root 2, and it's going to be our cos of, now this becomes 2 pi upon 8, which is pi upon 4, minus I sine pi upon 4, and then the next one becomes cos pi upon 2 minus I sine pi upon 2, then 3 pi upon 4, and 3 pi upon 4, and the next one is going to be 0 times the cos of pi, sine of pi, and then it's a 5 pi by 4s, and then 3 pi by 2, 3 pi by 2, 7 pi by 4, 7 pi by 4. So all we're doing is just working our way round the circle intervals of pi by 4. So let's go ahead and the next page and we'll see what the values of these turn out to be. So we're left with our f of 1 equaling 0 plus 1 upon root 2 times 1 upon root 2 minus 1 upon root 2i plus 0 minus I. I won't read out the rest of them so you can see them all written down there. Now this is going to give us half minus a half I plus minus I plus minus a half I plus a half minus a half I minus minus a half I. So now when we add these together, you'll see that the half cancels with a half here and the half cancels with a half here, so there's no real component here, and all we have is the I components, and when you add up the I components you get a value of minus 4i. So that means that the f of 1 is equal to minus 4i. Now we're not going to do that with the rest of them. If you want, you can always work through one or two yourself, but it turns out if you were to work through f2 you would get 0, f3 would get 0, f4 would get 0, 5 would be 0, 6 would be 0, and you would have a value at 7, and the 7 would be 0 plus 4i. So if we were to draw this out, the discrete Fourier transform of this out, then we would have our k-axis here, we would have our f of k, and we would have a value at 1 Hz which would be minus 4i, and then we would have a value here which would be, well, that would be 0, 1, 2, 3, 4, 5, 6 would be 7 Hz, which would be a value of 4i. Now that's not quite what we actually want. We would rather just have one value here and have the height of 1 to represent the height of our sinusoid. So let's go ahead and we'll see how we can get that. So I have a minus 4i and a 4i. Now we don't want this 4i here because this is the leftover from the fact that the discrete Fourier transform is actually a periodic function. So we don't want this in here. And also we actually want the height of the bin at 1 Hz just to be 1, which is the height of our sinusoid. So what we do is we ignore this value here and we double the value that we have here. So that would then become minus 8i. And then what we can do is we can take the magnitude of this. So the magnitude of the 0 minus 8i will be 0 squared minus the 8 squared, the square root of it, which would be a value of 8. So then we would end up with this 8i here. But of course, this is too big. It should only be a value of 1i. So this is where the division 1 upon n comes in. So we're going to divide this by the number of samples. So there's actually 8 samples here which have made up this 8i. So if we divide this whole thing by a value 1 upon 8, so it's equivalent to multiplying it by 1 upon 8. So we're going to be left with 0 plus I. So it means that the magnitude of our final function is going to be 0 squared plus the I minus 1 squared, which is going to be a value of 1. And also the phase here is going to be equal to 3 pi upon 2. Now you can see the phase here because we're actually going to have our value of minus I. So it's going to be 0 I minus 1 and then a value of minus I. So that minus I is going to go round the 3 pi by 2. So the phase is actually 3 pi by 2. So the question then is that how is this actually representing the sine wave? So let's have a look at that in the next picture. So if we were to draw out the sine function in red here and the cosine function in blue, and we start off a value is equal to 0, we can see if we follow the red function here that when we get to this point here, this point here is going to be at 3 pi upon 2, so that's 3 pi upon 2. But notice the blue function here at 3 pi upon 2, if we then start at this point, so in effect this is the phase, it's the initial starting point. The initial starting point is here now, so you can see that this blue function at that starting point is actually a sine wave. So therefore we expect to see our discrete Fourier transform to have a pulse at a frequency at 1 Hz and to be a magnitude of 1, and the phase of that is going to be 3 pi by 2, which tells us it's going to be a sine wave. So just one more thing before we finish up here. You'll notice that the 1 upon n is associated with the forward transform here. And we deliberately derived it that way through the video series, so that whenever you work through this example here, you'll be able to see where the division by n comes into the actual example. But generally, whenever you see the discrete Fourier transform written down, the 1 upon n is actually associated with the inverse transform. But it doesn't matter because it's equally consistent both ways. In the next video we'll look at the fast Fourier transform. So that is a generic name given to a family of algorithms that calculates the DFT. So thank you for listening. I'll get in the next video. Goodbye.